Good morning, everyone. I think we've reached that time at the top of the hour here, so we're going to start our webinar on 5G radio access networks, sponsored by Electrorent and Viavi. So good morning to everyone, and just a couple of quick introductions that we'll do here, and then we'll get underway. My name is Steve Case, and I'm with Electrorent. I'll be the moderator today on the webinar. And today we have Eduardo Anunza, and he's with Viavi and been around quite a bit and started in Viavi in 2012. Welcome, Eduardo.
Thank you, Steve.
And right before we start, of course, we're going to have a little commercial about Electrorent because we're sponsoring the webinar here today. So we're a large test equipment and technology services provider with offices all over the world. Most of our inventory is in the US and the UK and China and in Penang. So we have lots of equipment. If you have jobs overseas, well, we can help you out definitely. So and that also means we have lots of assets located all over the world. If you need something special that may be in another outfit, we can bring it over to your locale to get that asset there for you. And that's about us. So today we're happy that we're going to have a special giveaway, and the giveaway is for a digital inspection probe from Viavi. And this is a P5000i. It's not a new one. It's been around, but you know, worth about $2,400 when it was new. And we're happy to give this away. We just like everybody to hang around, answer a couple of questions in our survey and a quick poll, and then you'll be entered in automatically to win this cool prize. And so with that, I think we'll get started here. Eduardo.
Okay. So I'm going to start then with the 5G carrier and beam profile. Then I'm going to be talking about all different aspects, but I think this is going to give us a good foundation of what to expect, how signals are transmitted, how they look like, and what's different from perhaps LTE and some of the other technologies that we used to have and analyze. So first and foremost, some of the basics of it, it's how is the communication mode of the signals. And this is because traditionally we have seen LTE, and even for that matter 3G, and even back in the day with GSM or CDMA, typically all of them were in the low band, meaning anything between 600 megahertz probably up to 2.3, 2.4 gigs. And the communication mode was FDD, meaning that it was frequency division duplex, that it was one specific frequency or channel for the downlink. Downlink is basically a signal transmitter from the cell site, and a different frequency allocated or assigned for the uplink, or basically all the signals transmitted from UEs or mobile phones back into the cell site. In the case of 5G, though, that's going to change because now we're going to be going over into the mid-band. Mid-band is, as we probably know, all the C-band auction that we recently went through, and that's going to be around 3.74 gigahertz. And the communication mode, it's going to be on TDD, or time division duplex. What that really means is that we're going to have just one frequency that both uplink and downlink are going to be transmitted. So as you can imagine, we're going to have specific time slots associated or assigned for downlink and uplink. So it's going to be different in that regard. The other communication mode that sometimes we see is a supplemental downlink. So we can keep the same communication that we have, either FDD or TDD, but in addition, we have another channel that we're going to be using primarily for a supplemental downlink. And we're seeing things like these, I don't know, probably 2-3 years ago, we saw it with LTE and this whole concept of license assisted access, that basically we had our LTE signal and anchor, and in places where we have, for example, Wi-Fi spectrum available at 5 gig, we were able to use it. And by that I mean LTE signals were using the Wi-Fi spectrum to provide supplemental downlink. Something similar to this is going to happen with CBRS, or the new band just below 3.5 gig that we recently also went through. And specifically for 5G, however, we're seeing different deployments. One around the low bands, which also is going to be around FDD. Some other one that actually is going to be based on sharing the spectrum, also called a DSS, or dynamic spectrum sharing, which actually it's going to be an FDD approach, but here the channel is shared between 4G and 5G. And in mid-band and even in ultra wideband or millimeter wave, everything is going to be TDD based. So this is just, again, just as introduction on how the different communication modes are happening and what to expect in 5G. So moving along, just grab these from 3GPP. Again, just from a standards perspective, they define two frequency ranges, frequency range 1 and frequency range 2. In frequency range 1, you can have different communication modes based on different bands, and everything that is between 3 and 5 gig, all of it, it's going to be based on TDD, as well as in frequency range 2 or millimeter wave. And again, here down below, I just put an example of what we're currently seeing being used by mobile operators. 5G with dynamic spectrum sharing, basically leveraging the spectrum that they have with LTE, FR1, and the communication mode is FDD. And then in the C-band, in millimeter wave, everything is going to be in TDD based. Right, so 5G, what actually changed? I'm not going to go into all the specifics. Just let me just grab some important aspects of it. So here in the top left, we have the channel itself. As we have visibility of the channel with spectrum analyzer, so we have frequency against power. Here we have a channel. The channel, just like in LTE, is an OFDMA signal, meaning that we have a lot of different subcarriers being transmitted out. And the channel, just in comparison with LTE, here in 5G, it's going to be much wider. So in LTE, the channel was up to 20 megahertz. That was the maximum. We have seen some variations of 5, 10, 15, and 20. 20 being the max, and sometimes mobile operators have more bandwidth or more spectrum available, and for that they were basically aggregating channels. It was a little bit of a cost because those channels also had the overhead. Nevertheless, it was that approach with LTE Advanced of aggregating multiple channels if the spectrum was available. In the case of 5G though, now we can have channels that are as wide as 100 megahertz for FR1, meaning everything that is between 450 and 6 gigahertz. And then in frequency range 2, as you can see, we can go all the way from 50 to 400 megahertz. That's key. That's one of the key differentiators that we're seeing for 5G. Now we are going to be able to fully utilize much better the channel with data instead of just having multiple overheads with controlled signals. The other aspect is that is not a fixed size of the subcarriers inside of the channel. So we have here different options. Again, just as a point of reference, for LTE, all these subcarriers were only 15 kilohertz. Now we have the ability to make it 15, 30, or 60. And basically what that really means in reality is that we're going to be able to have the network to be more responsive. Because if we expand in frequency, we actually can contract in time, so the network is going to be able to be more responsive. And that was one of the other specific premises for 5G, to be low latency. And this is just the aspect around the air interface with which that is achieved. So just I wanted to mention just a couple of aspects of it, but the last thing that I want to mention here on this slide is that here we have power versus time just in the middle section of it. And as expected, and as I mentioned before, in the case of the C-band and millimeter wave, everything is TDD based. So we're looking in time, we're going to be looking into some periods of time or slots in which downlink is going to be transmitted, and some of the times in which the uplink is going to be transmitted, and so on and so forth. Okay, so, and actually talking about TDD and this uplink downlink arrangement, I just want to point out that is basically defined by the standard on what's the format in which the signal is going to be transmitted. Yes, I've said that, however, we have about 56 different possibilities of transmitting the downlink and uplink in TDD. And basically all the mobile operators might pick one or multiple of these configurations to send a transmission. So in any case, I want to point it out, and I have a couple of examples that I want to share with you, because when it comes to the ability of analyzing the signal, and probably more importantly, if we have a problem with that signal and we want to assess what the problem, for example, interference, that might be. If we have combined here the downlink and the uplink, it's going to be very difficult to find that interferer, because the downlink might be masking that interferer. So I'm going to elaborate a little bit more on that later. So just from a spectrum perspective, typically we used to have just a traditional spectrum analyzer, swept-tune spectrum analysis. This is a 5G signal example. Here we have a channel bandwidth of 90 megahertz. And as you can see, if we're looking into the signal, just because not always the pilots are transmitted in 5G, we see this fluctuation on the spectrum because, in essence, the signal is being transmitted in different time slots. Now, on the right-hand side, you can see a different approach of visualizing TDD signals, and that's with a real-time persistence spectrum. So this is a very good approach of having that visibility, because here we keep a little bit of the history of the signal itself. So even though signals might not be present, if signals were present for some period of time, here with a different color code, we can find the channel itself and have much better visibility. So this is just a new technique that now we have, and for that, let me just give you a quick example. So here I'm going to be making a measurement, and as you can see, this is a TDD signal. You can see that it's fluctuating up and down, control signals, because of, again, the difference between the uplink downlink. I'm going to be doing some trace management, meaning I'm going to be associating different traces based on power levels. I'm going to be basically setting trace 1 to have a max hold, trace 2 to be real life, and then trace 3 to have a min hold. So typically with this trace management, we had some sort of visibility of the channels. So now we have 2 different channels, both of them TDD, and again fluctuating. In comparison, now I'm going to be using a real-time spectrum. As you can see now with real-time persistence spectrum, without doing any trace management, I have visibility of both of those channels. So clearly, real-time persistence spectrum gives us a much better visibility of the signal. So this is just a new approach or a new methodology to test for TDD signals. Okay, so that's in terms of the signal itself and the channel. Now I'm going to be spending just a couple of minutes talking about the beams. In 5G, we have a number of beams that can be transmitted, and those beams, in essence, are the coverage beams or the SSBs. So this SSB is where the synchronization block that includes a broadcast, primary, secondary sync signals are transmitted. Each beam has its own SSB. And here, in comparison with, for example, LTE, in LTE we had different reference signals for each of the antennas. Those were transmitted across the entire channel. In 5G, that is not the case. In 5G, the SSB is just a subset of the channel. How wide is that signal? And actually some of the examples of the deployments that we have seen is here on the right-hand side of the table. I'm pointing out basically we're seeing, actually we have seen 15 kilohertz 5G signals that basically are just narrow signals of 5-10 megahertz that the mobile operators have decided to transmit in 15 kilohertz. So the bandwidth of that SSB, as you can see, is 3.6 megahertz. Now, probably the most common one that we're going to be seeing in the C band, it's going to be with 30 kilohertz. So the SSB, even though the channel might be, for example, 100 megahertz, the SSB, it's only going to be 7.2 megahertz. And in terms of millimeter wave, it's either 28 or 57 megahertz wide. Okay. Now, the other aspect of these SSB is that not only is a subset, but also might have an offset. So basically here in frequency might be at the center of the channel or might be shifted to the left or to the right of the channel itself. So that's basically an offset. And that offset, it's also been defined by typically by GSCN or a specific channel that is associated with the SSB. And this is basically the SSB, again, is my primary pilot signal that all the UEs first need to attach. And then based upon the different location, I might going to be using one or multiple of these beams. So anyway, I want to point it out, this other difference that we see on 5G. And here a bit more specific. Here's basically how the SSB is composed of primary, secondary sync signals and the broadcast channel signal. And again, the same type of bandwidths that we see based upon its configuration. And now in time, on the right-hand side is basically, according to the standard, where those beams will be transmitted and where in terms of the frame of the signal. So let me give you a couple of examples here. First, this is probably going to be applicable for the C band. So 3.5 gigahertz, typically we're going to be seeing a subcarrier spacing of 30 kilohertz. So all the beams, and actually in 5G, we're going to have up to 8 beams on the C band, or 3.7 gigahertz. And the distribution of those beams is going to be in time. So here on the right-hand side, I'm just showing you an example of a 1 5G frame. And as you can see here, the distribution of all those beams. In comparison now with millimeter wave or ultra wideband. And as you can see here, this example is with a subcarrier spacing of 120. And as you can see here in millimeter wave, we can transmit up to 64 beams. So not only we have more beams, but as you can see here on top, the number of slots that you have on the same subframe, it's significantly higher. So again, that basically is also can be translated on an air interface that is going to be more reactive or lower latency than in different subcarrier spacing values. So again, just wanted to give you a sense or an example of how the signals are transmitted. So how do we have visibility of the beam or the beam profile? Here I'm showing you a couple of examples. Both of them are in the mid-band, actually 2.6 gig and 2.5. And the bandwidth of each one of them is different. On the left-hand side, I have my carrier that is 20 megahertz. And as you can see here in the center, we have the SSB. The SSB at 30 kilohertz, so it's wide as 7.2 meg. In comparison with the right-hand side, and as you can see, I'm just using my real-time persistence spectrum to have visibility of my SSB. On the right-hand side, I have also my SSB at the same width of 7.2, but now the channel is wider. Actually, I have my bandwidth up to 80 megahertz. So the channel here, specific one, it's about 60 megahertz. So again, with persistence spectrum, we have visibility, and we're going to be able to characterize much better the carrier itself, as well as the SSB. And by that, I mean that we're going to be able to have visibility of the channel power, as well as where the SSB is located. And some of the times we have heard, hey, we have connectivity problems with 5G. And first and foremost, we basically look into the spectrum. We look on the amount of power that is being received at that specific location where problems are happening. And sometimes we see problems with power levels. And some of the times we're seeing problems that the SSB is not where it is expected to be. So as an example, in one location, we might have that one radio is transmitting the SSB aligned with the center frequency of the channel. Just in the other radio, it is expected to have a soft handover. The SSB was or had an offset, and therefore we're having some problems of not having a soft handover, but having a hard handover. So things like that are very useful to characterize the proper profile of the carrier and the SSB. Now, before I move into the next topic about interference, I'm just going to pause for a second and see if you have any questions so far.
We don't have any questions. There are a couple of questions about getting the slide deck, and we will have the slide deck available for everyone after the presentation and before the survey and the poll. So just hang in there. We'll present that to you. It'll be in the handout section. But there were no technical questions. So, and if you do have questions, people put them in the questions section of the webinar, and every couple minutes we'll go back to Eduardo and he'll answer them for us, but not right now.
Okay, thank you, Steve. And I just touched on some of these aspects briefly and probably too quickly, but yeah, feel free to post any questions you might have. Now, in terms of interference, as I said, one of the main problems that we are seeing not only with LTE, but also with 5G is the presence of interference. So interference is basically any other transmitter that happens to be at the same frequency of the mobile networks. And to be a bit more specific, interferences that are happening against the uplink. And that is because typically the cell site can transmit a much higher power than the UE or the mobile phone. So if there's any interferer or any other transmitter that happens to be transmitting at the same frequency, the power of the cell might overcome that interferer, but not so the power of the UE. So that's why typically we're looking for interferers in the uplink. Okay. And certainly we have different types of interferences. Here on the right-hand side, I'm just showing an example of, okay, so we have an uplink. I actually put on my persistence spectrum just to have full visibility I put a max hold, so as you can see the complete channel there painted on my trace of the uplink, even though we have different physical resource blocks transmitted. I just, for some period of time, put my trace on max hold so we have full visibility of the channel. And as you can see here as well, we have an interferer that is right in my uplink. So that's basically one of the things that we want to find first, to identify the type of interferer, and second, to find it and then basically mitigate that interference. So how do we do that? So first, typically we're seeing three different types or categories of interfering signals: wideband, narrowband, and frequency hopping. So I have here an example of those interferers. So I'm going to start with the wideband interferer. So as you can see here on my spectrum, I'm looking into this wideband, and just by using markers, I can see that it's roughly about 6 megahertz. So this is a typical problem that we see with mobile operators with digital TV, that when that is a leakage that happens. Narrowband is another one that it's common. And then the third one is frequency hopping. So we have transmitters that do not stay in one frequency, but they hop in a different frequencies. And we've seen that with welding machines and some other industrial equipment that are difficult to catch because they change in frequency. So in any case, these are the three main categories of interference signals. Right. Now, what's going to happen if that interference signal happens to be on TDD transmission mode? So again, we might have an interference, but since we have it on that carrier that has uplink and downlink on the same frequency, as I mentioned before, probably the downlink might overcome the power level of the interferer, but when it hits the uplink time slot, that is going to affect the communication with the mobile. So the way basically to have visibility and properly identify those interferences is with a specific triggering of the spectrum, and that's being called a gated sweep. So on a specific time gates, we're going to enable the spectrum, and to be more specific, the gate is going to be on the uplink. So basically here the intent is only to have visibility of the uplink signal. Therefore, we're only going to be looking for uplinks, and we're going to be avoiding the time slots of my downlink. So in that way, we're going to be able to have visibility of potential interference. So here on the right-hand side is basically an example of the gated spectrum. And first, we see the signal on a time domain. So in essence, we're kind of seeing the signal from a time and looking into those different slots between uplink and downlink. And we have two gates, each one of them on the uplink sections. And those are the gates where we're going to have the frequency view or the spectrum view of the signal. And we basically here, we're going to be able to then have just visibility on the uplink and effectively being able to identify interferers. So let me give you an example. So here we have a couple of TV signals. I'm using my real-time spectrum. And then in one of them, I'm going to be using gated sweep. So again, triggering the spectrum on a specific times. And as you can see, I have seen the uplinks and I have put my gates. One important aspect of this measurement, however, is that all of them needs to be referenced with GPS. So we're not going to have any deviation or variation in time. So I have my gates, and then frequency domain on the spectrum, I only have visibility of the uplink. And as you can see here now, having just the uplink, I can analyze a signal and then find that we have a specific interferer on that frequency, 2.53 gigahertz. So clearly, this is a methodology that it's going to be very useful for finding interferences in TAD signals. Right, okay, so now that we have found the interferer, what's next? Next is to find it, to hunt for that interference, to see the location of the interferer. And for that, basically, we just use a solution that with a drive test is going to create a heat map of that interferer. So while we drive around, it's going to give us or point us into the location of where that is the interference coming from. So that's basically what we call our interference advisor, but in essence, it's going to be working in conjunction with a spectrum analyzer to find the interferer. So let me just give you another quick example on how that is performed. So first, here we have connectivity with our spectrum analyzer, and this is done via Wi-Fi. The setup is basically all done being in a car, since we're going to be doing a drive test. Then the solution has connectivity to the internet, so we're going to be able to have a map. At the same time of the map, we're going to be able to find or assign specific tracking modes based on type of interferer. Again, wideband, narrowband, or frequency hopping. Once we define that tracking mode, we can just start driving, and automatically we're going to be able to see the signal strength of that interferer, and it's going to give us a bearing or a direction on where is the location where the strongest signal was received, and that is the strongest interferer signal was received. So again, just with continuing driving, we are going to be able to find the location, and then typically for these needs to be properly documented. So automatically we can just make a report out of it with the measurements and the location of that interferer, and then with that document, then later on we basically the mobile operator can go and shut down or do a further analysis, finding the device that is causing interference. So that's the ability to not only find the location, but also have the ability to properly document it to then later on mitigate it. Okay. Okay, so next is propagation and coverage. And this is also an important aspect because just again, in comparison with what we're used to deal with low bands, is not going to be the same with mid bands, and certainly not the same with high bands. And basically what I'm referring to between the low, mid, and high is low bands and anything below, let's say 2.5, 2.6 gig. Mid is in the 3.7, 3.5, and then high it's millimeter wave. But what's the difference? So the difference is that if we just look into the free space path loss, and I have a table here on the right-hand side with different frequencies. As you can see, the first one is if I transmit at 751 megahertz, I have a free space path loss just because of the air that we have. We have a loss of about 82 dBs in 400 meters. In about a mile, we have about 94 dBs of loss. Okay, but now what's going to happen if we go up in frequency? So let me just go all the way up to what I have there highlighted in red. So that's for the C band, 5G C band, so 3.7 gigahertz. And as you can see, in a mile, I'm going to have a loss of 108 dBs. So that's significantly more than what I used to have or used to deal with in the low band. And certainly we go now into the 28 gigahertz. Now in a mile, I have 125 dB of loss. So again, just something to keep in mind in terms of what to expect for the different frequencies that are transmitted. Now, the other aspect is what I call shadowing. Shadowing is basically the ability for the signals to go through different materials, perhaps. And when the signal goes into those materials, the scattering, dispersion, absorption of those, and what to expect. Actually, I'm probably going to go into a bit more detail on shadowing a little bit later. But the other aspect that I wanted to point out here is the relationship that exists between the frequency ranges and the number of beams transmitted. So here in this example, I have in a cell, I have collocated 4G and 5G. 5G, I just exploded a little bit to have a better visibility of the antenna panel. And in this example, I'm just showing that we have 64 antennas, or 32 cross-polarized antenna elements. We might have multiple panels, by the way, on the radio. This is just one of the examples. So again, this is going to allow us to have different number of beams available, and with a higher number of antennas, we can shape those beams much better. So at the end, according to the 3GPP, how many beams can be transmitted? Well, we can transmit, if it's in frequency range 1 below 3 gigahertz, we can transmit up to 4 beams. If it's between 3 and 6 gigs, so the case of C-band, up to 8 beams. And then in millimeter wave, we can transmit up to 64 beams. Okay, so what's the benefit of all those beams? Well, the notion is to have all those beams associated to different areas. So we have, for example, a near field, mid field, and far field. And different beams are going to be assigned to each one of them. And here the goal is to have what is being called a 3D beamforming. So not only vertically, but also horizontally, we're going to be able to assign different beams. So in that way, we can have different customers or UEs connected to the radio, moving from beam 1 to beam 2. For some specific area, the same beam might be adjusted, but if it goes beyond the area of service, it's going to be switching over into a different beam. But again, the goal is to have full coverage vertically and horizontally. Right. Okay, so now a little bit more on shadowing. And what's the difference in shadowing on different frequencies? So we have here my 5G radio, and based on the environment, well, different materials that we might have in front of the radio, is how far the signal is going to be able to go or to travel. So I just give the example of the free space path loss. That means basically a free space, no obstructions, no materials. If we add here different materials, and I have had it on different frequencies, so I have here in the table different materials. I took these actually as an example from 3GPP, from glass to concrete and wood. And then what's going to be the penetration at different frequencies? So low band, in this example that I use 750 megahertz. As you can see, the reflective glass was probably the highest, but as you can see here in wood and concrete, it's between 8 and 5 dBs of loss. So it's manageable, certainly. However, if we go up in frequency, for example, 3.75 gigahertz, we see now a bit more severe loss on concrete elements, from 8 to 20 dB of loss. And certainly, if we go all the way up to millimeter wave, 28 gigahertz, as you can see here in concrete, basically the signal is totally blocked. We have 117 dBs. And in wood, 8 dBs. Actually, I have to say, though, that in some of the tests that we have conducted, if we have a radio, and these radios in millimeter wave typically are in small cells, if they have a tree in front of it, they have multiple kind of wood materials that the signal based on what we have seen on trees is probably a loss of anywhere between 10 to 15 dBs. So is significant. So in reality, what we have seen is that in low and mid bands, the biggest interference problems are with external interferers or even passive intermodulation. In the case of millimeter wave, though, the biggest problem is not that, but obstructions. So materials or buildings or billboards or anything that later on people put in front of the radio, and that it's severely going to affect the coverage of the small cell in millimeter wave. Okay, I want to close out with how we look into the signal quality, but before I do that, let me just again pause for a second and see if there are any questions.
And we do have some questions. So I'm not sure if we're going backwards or not, Eduardo, but maybe our folks have their thinking caps on, and so we have some questions. So the first question is about how to do initial patch and handover. I'm not sure if we're covering that here today, but that was the question.
Yeah, so the initial one is basically when the UE starts looking into the broadcast beam, the SSB, and that's the initial connection, let's say, that exists between the mobile and the cell site. And with that, it's going to be able to get all the specifics. So out of the SSB, it's going to be able to get the SIB and the MIB. So basically all the characteristics of the carrier and the SSB. And typically when that happens, it expects that to be consistent among the different sectors and among the different radios. So it's going to have different neighbor lists of cell sites, and then it's going to be able to transition that over. And we've seen problems just because, again, on the next sector, basically it has, just because of not a proper configuration, it has a different SSB that is not expected by the UE, so it needs to reconnect. Yeah.
So there's a couple of follow-on questions for that one. Did 5G define RHCP and LFCP for transmit and receive?
They do, yeah. So there's different default values, and that's the initial connection that the UE establishes. And then later on, based upon that information that it receives, then it can reconnect on a different configuration.
Okay, and then two more questions regarding the antennas and beam pointing, which is the omnidirectional antennas are very different for LTE. So I'm not sure if I got that question right.
Yeah,
But,
so before in LTE, it was basically commonly used to have a single antenna, and sometimes when you use an omni antenna, just a single antenna transmitting signal everywhere. Now with 5G, since we have multiple beams available, then we can have, or we must have, different antenna elements from which we can construct those beams. If you only have one antenna, then basically that antenna, and I'm talking about one antenna element, it's just going to be one beam broadcasting everywhere. But if we have an arrangement of multiple antenna elements, then we can construct beams based on different phase and power. So that's probably the main difference now with 5G, that now we have more beams available. And we have, instead of just omni, we have panels or even cylindrical antennas, but inside of them, there are basically panels of multiple antenna elements that we can construct multiple beams.
mm-hmm. Okay, so we have an interesting question here, and it's let's see. I'll just put it out there. It says some carriers claim they can use an 800 megahertz channel for millimeter wave or FR2. And is it because of they're using carrier aggregation? So I think maybe they have a couple of concepts cross-connected there, but I'll put the question to you, Eduardo.
Oh, okay, right. So what we have seen is that in ultra wideband, they are using 800 megahertz of bandwidth available, and that bandwidth it's on that band of say 24, 39 gigahertz.
That's a lot of
And
bandwidth.
it is a lot of bandwidth. Yeah, they got a lot of bandwidth available. And now how they're doing it, how they're using it, and sure enough, they're using it by transmitting 8 carriers, each one of them at 100 megahertz. So they are occupying all that bandwidth with aggregating 8 different carriers. That's
Okay.
typically how they're doing it.
Interesting. All right, I think we've covered all of them. So why don't you continue?
Okay. Okay, so looking now into signal quality. And again, this is just a way, this is the instrument that we're using, the either the Cell Advisor 5G or One Advisor of Viavi. This is basically how we have visibility and how we have conducted all the measurements and the examples that I have shown you with real-time spectrum interference and so on. And it's the same tool that I'm going to be here sharing with you some of the examples about the signal quality assessment of 5G. So let me just go into it. First is the ability to have visibility of multiple 5G carriers, even though they might be at a different band or the bandwidth of that carrier is different. For example, here I'm showing a couple of carriers. One is at 885. Actually, this 5G signal, it's out of DSS, or dynamic spectrum sharing, and the other one is in C-band. And certainly here we can have also set it up to look into millimeter wave. But what's the benefit of this? So the benefit here is that a specific site might have different 5G signals available. So collocated, they're going to be able to have DSS, C-band, and even millimeter wave. The goal or the purpose here is to have this ability of how much power is coming out of each one of them. And not only that, but here on the right-hand side, here is basically the beam quality. Beam is basically here in the broadcast channel. We have visibility on how good the symbols are transmitted. So those dots that you see in each quadrant, those are the symbols on QPSK for my broadcast signal. If it's over the air, anything around even 25%, it's acceptable. But sometimes we have seen a lot of distortion, even though the power level is okay, and that typically is due to interference. So certainly a good quality indicator is this constellation diagram, because again, regardless of the power, the quality is not always as good as it should be. So in any case, this is one methodology, one way to have visibility of my carriers. And just on the question that was asked about aggregating multiple channels in millimeter wave, up to 8 of them, here in the same manner, we can have 8 different carriers for each of the channels in the 800 megahertz bandwidth that is being used, and have visibility on all of them, expecting that all of them will have the same power level. Okay, the next one, it's the number of beams that are available. So here on the left-hand side, I'm showing what we call the ID scanner. Here we have not only the beams coming from one sector or one radio, but also might be beams coming from 2 or 3 radios based upon the location. So we have an overlap. So sometimes we move, then we should have visibility of multiple sites so we can do a soft handover. Otherwise, if we lose visibility, the call is going to drop. So in this example here on the left, I'm just showing each of those sets of 3 bars. That's basically the characteristic, if you will, of the SSB or the beam. So the first one and the second one is coming from the sectors 48, 49, and the third one is sector 50. So basically 3 different sectors. And then on the right-hand side, I'm just showing how many beams are available. So here in this example, I have my signal. Actually, this happens to be in the C-band range. I think this is at 3.7 gigahertz. As you can see, the bars, all the bars represent a beam. So we can transmit up to 8 beams in this band. And as you can see, only 1 beam is transmitted. All the other beams are non-transmitted. And we have seen these with mobile operators that sometimes, even though they have the ability to transmit 8, they only transmit 1 or 2. And similarly, millimeter wave, even though they might have the option or the ability to transmit 64 beams, they just transmit a subset of those 64. In any case, in addition to that, and similarly to the channel or the carrier scanner, here we can just set to make an analysis, a quality analysis or a quality assessment of that beam. And as you can see here, I just put my marker on that beam, and down below I have the specifics and as well the beam quality. And again, very useful not only to assess how strong the signal is coming, but how good the quality is of that signal. And then one of the other things that typically we're seeing with customers is that the spectrum, it's so populated now with different types of signals that sometimes they have difficulties finding where they are and what type of signals they are. So in this example, I think I just tuned it between 700 and 900 megahertz. So as you can see, in this specific location, we have different signals. Actually, 3G, 4G, and 5G. And to be more specific here, most of interest is 4G and 5G. As you can see, 2 of them are present. And actually a third one with DSS. DSS, 10 megahertz wide, and I have 2 LTE and 5G on that same carrier. So for that, now we have the ability to do what we call a blind scan. So we just define the frequency of interest, and automatically then we'll be able to get the type of carriers that are on that band that we defined. And not only that, but we're going to be able to know the frequencies of each one of them. So as you can see here, we have 1 NR and A72, and then a couple of LTEs, and actually one of those LTEs happens to be in DSS. So anyway, this is just a way that we're making things easier for people interested on the air interface to find the different channels that are transmitted. Right, and then the last point that I want to touch on is coverage. And as I mentioned before, sometimes we have a lot of problems with penetration. And certainly it's important to do either a walk test or a drive test to have an assessment of coverage. In this example, actually, we have the ability to track multiple signals at the same time. In this example, I'm tracking 1 5G signal and 2 LTE or 4G signals, all of it at the same time while I'm doing this drive. And again, this is convenient. This is typically done in 5G non-standalone, because in non-standalone 5G, it has dependency of availability of 4G, because in 4G, all the control signals are exchanged. And once all the control signals are exchanged, then the data can be transmitted and 5G then is going to be used. So again, very useful for finding anchors in LTE for my 5G non-standalone. On the right-hand side, it's a similar example, but here it's been, actually this test was done indoor And again, I'm tracking both 4G and 5G signals at the same time, and I have the ability to have the signal profile of each one of them. Right. Let me close out with this slide. This is basically kind of a summary of what we call best practices that we have seen being used by different customers and mobile operators in 5G. And I think I did briefly touch in each one of them. So first, the carrier profile of my signal, how strong the signal is and the bandwidth of my 5G signal. Beam profile, how wide is my SSB or my beam, and if I have a frequency offset. Then possible interference that I might be seeing. Beam forming, this is how many beams are available at different locations. And last, coverage, not only coverage on 5G, indoor, outdoor, but also coverage of 5G and 4G at the same time concurrently. So I will have ability to have an assessment of non-standalone. So with that, I want to, well, first, thank you all for attending. And again, if you have any questions, please let me know. I also put a link if you have more questions or would like to get more information. I put there just a link of our 5G test solutions. But Steve, don't know if you have any other questions for me.
We had one more. I think we have a couple of minutes here, like 3 minutes, and
yep.
Taking up the whole time. So thanks for everyone for hanging around and doing this. Here's one question for us. Is it possible to move the SSB position in the spectrum?
It is, for sure. And we have seen different cases that the SSB has a different location in the carrier. Sometimes we have seen it at the left, at the very beginning of the carrier, or shifted, or at the center. So it's configurable, yes. And probably we're gonna see that a little bit more later on when the industry is gonna be adopting the ability to do bandwidth parts. So basically, they can change not only that one carrier is going to be occupying one specific band, but it can be partitioned in different carriers on the same band. So it all depends on the traffic that we have in certain areas. Quick example, on a stadium, and we have a big event, then there's going to be a big channel with one SSB in a certain location. Now, if we don't have a big event, certainly the mobile operator might want to lower that down significantly to avoid a lot of power consumption, and it can be partitioned that in different bandwidth parts. So the channel is going to be much narrower. So the SSB also is going to change, or from the very beginning, it's going to be at the left, for example, of the carrier. So when the bandwidth part happens, the SSB is going to stay the way it is. So anyway, different approaches, but yes, long answer, but it's configurable.
And related to that, is uplink traffic better to put in an extreme position?
Uplink traffic, well, it all depends on the scheduler, but I don't think it exists a specific location. Perhaps the only thing that I have seen that might give an indication or a guidance on where to put uplink, that it's when you have in a band. I've seen cases where in the around 2.5 gig, there were some other bands or some of the signals present on the same 5G band. So as an example, there was one LTE next to my 5G, and sometimes you might have an RF leakage or even PIM out of LTE that might be affecting my 5G carrier, my 5G signal. So you might want to have a little of a gap or a guard band or a blank PRVs. I think that's the terminology being used to allocate traffic to avoid interference on that modality. And And that's just for some period of time until they fix that problem. But anyway, that's
Great.
probably an indicator.
Eduardo, thank you for giving this. It's extremely informative. Plus, we had a lot of good questions too, some that even surprised me. But I learn every time we have one of these. So thanks everybody for coming, and thank you, Eduardo.
Yeah, thank you, Steve, and thank you, everyone.